talked about what the MA circuit was when we actually got mass. The MA and time are controlled separately. The MA is what we use to control the heating of the filament, and therefore the space charge, the electron cloud that we create before we make an exposure. So the higher the MA, the more electrons we put on the filament, the hotter it gets, but also the more electrons that we're going to send across the tube. There's a direct relationship between MA and the tube output once we make our exposure. So we talked about what we need to make that happen. We have to have a different type of rheostat. We have to have a step-down transformer. We have to have very low voltage to prevent those electrons from traveling across the tube before we want them to. So we talked about time selection. Time selection is in a separate circuit. Overall mass is calculated as MA times time in seconds. We talked about what we call mass, that being quantity or intensity. So what it controls in the X-ray tube is, again, the heating of the filament. It controls your thermionic emissions. Once we make the exposure, it controls the number of X-rays that jump from cathode to anode. In the creation of mass, what we do is we get tube current. Once we get mass, until we make our exposure, we don't have tube current, we just have filament current. But we create a lot of heat compared to the amount of X-rays that we create. So we talked about the proportionality of mass to emission and interaction in the patient, interaction at the image receptor, and it's all proportional. It's proportional in every way. So as you increase either MA or time or both, then you're going to get a proportional change in tube current and image receptor exposure, patient exposure. Everything is proportional. You double your mass, you double the exposure all the way across the board. We talked a bit about reciprocity. You increase MA, decrease time, you can arrive at the same mass value. We talked about when we might want to decrease MA and increase time for a breathing technique. Those things would be like a sternum, lateral T-spine, wagging jaw, if you remember the Ottenello method in the spine. So there are times to use that, to use motion to try to get rid of some overlapping anatomy, but that's pretty rare. Most of the time we want to increase MA and decrease time in order to prevent motion, but there are times that we actually want to use motion. So we accomplish that with reciprocity. Reciprocity just meaning mass equals mass, right? So increase MA, decrease time in the same magnitude, and both of those, then we maintain the same mass, overall mass, and our exposure should not change. So we talked about mass and the effects on the brems spectrum, and that is just that we get an increase in numbers all the way across the board. So really the only thing that it changes is the height of the brems spectrum. It doesn't have any effect on anything else. Peak energy remains the same because KVP is the only thing that changes that. Minimum energy doesn't change because filtration is the only thing that changes that. Average energy remains the same because we increase every energy level proportionally. So the height of the bubble just goes up. Well, that's the only thing that changes. So effects on different types of exposure. Again, we talked about that. That was patient exposure, direct relationship. Image receptor exposure, there's a direct relationship. If mass value gets too low, then we could introduce quantum model, right? And also if it gets too high, we overexpose a patient, and you can get high enough in your exposure, specifically with mass, that you flood your image receptor. We didn't really talk about this, but you could flood your image receptor individual detectors with so much information that you can lose contrast. But that's an extreme exposure. You know, you accidentally set something like a abdomen exposure for a hand or something like that. So in reasonable exposure ranges, mass is not going to have just a whole lot of effect on the image itself, but we talked about the ethical implications of understanding your technique and not overexposing the patient. It became so prevalent for a while that we created a name for intentional overexposure, and we called that
Creeping.
Huh?
Is it creeping?
Yeah, dose creep. Dose creep. So that's what the brim spectrum looked like. So all that stuff we're going to reinforce this semester. We're going to just beat KVP and mass specifically to death, and how to manipulate KVP and mass, and how to use it whenever we're need to change our technique because of other equipment. All right. So voltage rectification, we talked about that. Voltage rectification is changing alternating current to direct current, and it occurs in the high voltage section because we need that alternating current to make all of our transformers work. It doubles our tube output, so we have, instead of having alternating current and losing that negative side, we actually utilize that. We not only rectify, we not only transform alternating to direct current, but we utilize that negative side so that we send the entire voltage waveform across the X-ray tube. So it doubles it. And really the effects on the generator, or the voltage waveform is, again, it's going to look an awful lot like our increase of mass. It's just going to increase the numbers. So generator type, we had 3 different types of generators. We had single phase, 3-phase, and high frequency. And with each one of those, our voltage ripple goes down so that we get a smaller number. Our voltage ripple for single phase is always going to be 100%, regardless of its half wave or full wave rectified. Remember, full wave rectified means we're using the full wave, right? So it's rectified, and we invert that negative side so that we use the entire wave. And it's 100% voltage ripple on both of those. It drops to about 14% for 3-phase 6 pulse, and about 3% for 3-phase 12 pulse, and 1% or less for high frequency. So with each one of those, what we do is we increase the output of the X-ray tube, but we also increase the average. Peak energy remains the same, minimum energy remains the same. We get higher output with a higher average. So we get a better beam quality. Remember, what we use to control beam quality is KVP, but we get a better beam quality with a 3-phase and certainly a high frequency voltage waveform. All right, so we just talked about that. So we took a look at the difference between them: single phase, decrease output, lower average; 3-phase, increase output, increased average; high frequency. Again, it's pretty, I won't say insignificant, but it's not a great jump from 3-phase to high frequency. And we talked about our technique compensation for whenever we change from single phase, because single phase is a lower output if we change from single phase to 3-phase, and we've got a good technique for single phase, and we move to 3-phase, and we're going to have to change our technique, right? Likewise, if we go from 3-phase to single phase, we're going to have to change our technique, right? And that's always going to be a factor of 2. Okay, so that's where we left off. Any questions on that before we jump into the X-ray tube? So since we've done so much legwork on everything else, and we've talked about some of the stuff in the X-ray tube, this should go a little bit quicker. But, that depends on me being able to, tone it down some. So we'll see how it goes. So we have 2 different types of tubes. We really only use one. We have stationary anode, and we have rotating anode. We really only use the rotating anode type of X-ray tube. You might, if you happen to go to the dentist, I hope you go to the dentist every now and then, they do some X-rays. Their tube output is so low that the things that we use in diagnostic, they don't really apply to theirs. They now use, anybody been to a dentist's office who uses a little gun X-ray tube? That is so fascinating to me. They just got this little self-contained X-ray unit that they just pick up, and it looks like something off of a sci-fi movie, and they stick it up next to your face and they, zap you with it. It's digital, so they put a digital image receptor in your mouth and zing you with it. It's pretty wild. So inside this little thing, you've got everything that we use to make a high voltage X-ray beam, but it's all contained inside this one little gun. It's not little, it's kind of big, but it's, you know, compared to what we use, it's pretty small. So I can't imagine them having a whole lot of cooling oil or fans or any of that kind of stuff in there. It doesn't have a rotating anode. You don't hear it spin. So they're going to use stationary anode. That's one. And also they're going to use single phase unrectified unit. So it's got to be battery powered. It doesn't even plug into anything. So what kind of batteries are you using? I don't know. So that's about the only place that you're going to see a unrectified, definitely the only place that you're going to see unrectified X-ray tube. X-ray, if you remember, in dental, they call the dental tubes self-rectified units because they don't use any rectifiers, so the X-ray tube becomes a rectifier. That's still registry testable. For what reason, I can't tell you. I don't know. So we use rotating anode. We rotate the anode so we spread out the heat, right? The main thing we create in the X-ray tube is heat. Create the heat on the filament, send the heat across the tube, hot electrons across the tube, it's thermonic emissions across the tube, deposit them on the anode, and if we can rotate that anode, we can help to spread out the heat. Remember, we have 3 different ways to dissipate the heat. What were they? What's that? Oil, yeah, okay. We use the oil, but that's not one of the 3 ways that we dissipate. We dissipate through conduction. Conduction is spread by touching, right? So the stream of electrons actually touches a very small portion of the anode, but if we use a big round anode and we rotate it, the different portions of that anode, the disc, are touching, and so we can spread out the heat, right? And we used last semester, we used like cooking with cast iron. You put cast iron over the fire, and even if the fire is just hitting the pan and not the handle, can you reach down and grab the handle? Not unless you want blisters, right? So the heat spreads out, we get conduction, and then we get, if you're drinking something like, I don't know, coffee or hot chocolate and it's too hot for you, what do? Blow on it. Blow on it, right? So you're moving air across it, and that's what we call convection, right? And the other is the transfer of energy through space, and we talked about that, not really beginning with this, but earlier in the semester when we call transfer of energy through space, radiation. All right, so we get thermal radiation. So we use all 3 of those. And in the rotation of the anode, it helps with that conduction. All right, and then we had a number of different parts to the anode, the target just being a portion of that. Not even the entire disc is what we consider the target. The target is just where we bombard the target or the anode with the electrons, right? So we've got a lot of stuff going on with the anode into the X-ray tube. We have the target area, that's what we call a focal tract. Then we got the disc, and then we got the stem, and the stem is where we get the rotation, right? And then even on the outside of the X-ray tube, we consider it a portion of the X-ray tube, and it's certainly a portion of the anode assembly, and that is your electromagnets, and they are responsible for rotation of the anode, right? So they're on the outside of the X-ray tube, but they're still considered a portion of the X-ray tube. So anode in, what is the rotor? That's pretty much everything that rotates. It rotates on ball bearings. The stator is on the outside of the X-ray tube. The stator is your electromagnet. The target is the area of bombardment, specifically the focal tract. So it's everything we just talked about. A cathode into the X-ray tube, we tend to focus on the filament, and the filament is a portion of the cathode, but it's not the entire thing. So the purpose for the filament is to provide those electrons. So it's the source of thermonic emissions, and we have 2. It's not for backup. We have 2 for specific reasons, right? So we've used the analogy in the demonstration of the kind of shadow you cast from fluorescent lights, right? You remember that from last semester? You hold your hand over your desk when the fluorescent lights are on, and what does your shadow look like? And you can actually see it outside today too. You walk outside and look at the ground whenever you leave. It's weird that just almost every time that I kind of lecture on focal spot size, it's a cloudy day. Walk outside and look at your shadow whenever you leave. And what you're going to see is you don't have much of a shadow, right? Because it's overcast day, so the entire sky becomes a light emitter instead of the sun, right? The sun's still providing the light, but it hits the clouds, and the entire sky becomes a light emitter. And as a result, you don't have much of a shadow at all, right? But and it's kind of like fluorescent lights, because the light comes from a lot of different directions. You don't have much of a shadow if you hold your hand over your desk. But if it all comes from one spot, what does the shadow look like? It's good, right? Right, so, and that's a kind of an extreme example, but a large focal spot, the purpose for the large filament is so that we can stack a lot of electrons on it, but what we lose is some sharpness of recorded detail. It's not going to be as dramatic as fluorescent lights or overcast day, but we do lose some sharpness of recorded detail with a large filament. What we gain is an ability to create high mass exposures. So I think I recommended this last semester. If you go into clinicals tomorrow and you don't, let's say it's it's kind of slow, right? Go into your x-ray room, turn off your phototimers, and set your technique, right? So select small focal spot size, and that's the button that looks like a small box inside is small focal spot. Select the small focal spot and then select 400 MA and see what happens. Unless you're working on some weird equipment, it's going to give you tube overload. At any mass value, it's not going to let you shoot with 400 MA. As for protection, it doesn't want to stack that many electrons on a small focal spot size. Click it over a large focal spot and you shoot all day long, okay? So small focal spot, you've got tube limitations, but you increase your sharpness of recorded detail. Instead of shooting like a fluorescent light, you're shooting from more like an incandescent light or a smaller, light emitter. Okay, so you have two of them for those reasons. One for large exposures and one for sharpness of recorded detail. The focusing cup, the purpose for the focusing cup is to try to compensate for the natural tendency of the electrons. So all electrons have a charge, and that charge is positive or negative? It's all negative, right? So you take two negative things and you cram them together, and what are you going to have a tendency to do? Like charges repel, right? So if you put all those electrons on a filament, they're going to have a tendency to try to push away from each other, right? So the purpose for the focusing cup is to compress the electron cloud, the thermonic emissions, try to compress that, kind of pack them in so that they don't get too broad, so that also when we make an exposure, it sends the electrons across the tube and it just hopefully hits the focal tract, okay? Because whenever we hit the x-ray tube with high voltage, because those are all negative charges, if we don't have something trying to compress them and keep them close together as they travel across the tube, I used this analogy last semester. You drop a bowling ball in a mud puddle, and where's the mud going to go? Everywhere, right? So it's going to go everywhere. The electrons are going to go everywhere. But if you keep them compressed, it's kind of like, you drop the bowling ball in a I don't know, you got mud in a trash can for whatever reason. Is that trash can going to keep those, droplets of mud from going in specific directions? The answer is yeah. Okay, so that's the purpose for the focusing cup, is to try to keep those electrons compressed so that they go across the tube and they interact just with the focal spot or the focal track on the anode. The purpose for that, again, is to increase sharpness of recorded detail. If we didn't have that, then we're going to lose sharpness of recorded detail, probably even worse than if we were to use large focal spot. So it's, essential piece of equipment. All right, so filament circuit controls the filament current. low voltage, very low voltage. Filament current just to create your thermionic emissions. It's present all the time, right? We talked about that last semester as well. It's present all the time. Purpose for that is to keep your tube a little bit warm. So we always have filament circuit or filament current. It's just not high enough to get the thermionic emissions until we hit the prep button, right? So when you push the prep button, it increases. But what do we get when we hit the prep button? We get rotation of the anode, but it's specifically in the cathode, we get thermionic emissions. Thermionic means hot ions are boiling off of electrons, right? So the main thing that kills your X-ray tube is heat. We create a lot of heat. If you overuse your prep button, then you create heat, right? So same answer all the way across the board. So what's that going to do to your the life of your X-ray tube? It's going to reduce it, right? So we got a couple of things going on there. One is that you create so much heat that it can shorten the life of your X-ray tube, but also you can use prep so much so that your space charge is going to in part overcome the effects of your focus of color. Okay, we have a specific word for that, and that is in the springtime when your flowers, are nice and tight in a bulb or in a, what do you call it, bud, right? And then they open up and they spread out. What do we call that?
Bloom.
They bloom, right? So the same thing that we call in the space charge. If we overuse prep stage, that's what you call blooming. Now, before we press onto this, is there a time to hold the prep button down? Are there legitimate examples that you can think of when we need to be on that prep button longer than just that 1 second to get the anode up to speed? Kids, bingo. Kids, you got a screaming kid. If you're not on that prep button, you're not going to get a full inspiration. So kids, if you're in surgery, and I understand most of your surgeries are done with C-arms now, but if you happen to be working somewhere where you're doing plain, film radiography with an image receptor, it's not really film, but with an image receptor, you may need to be on that prep button. For example, if they're doing a cholangiogram, study for gallstones, they're going to inject some contrast. They're going to want you to shoot, but you've got to coordinate with the surgeon and the anesthesiologist. The anesthesiologist is going to have to suspend respiration so you can make an exposure. If you're not on the prep button, then you're going to kind of miss it. So there are times that you have to depress the prep button for an extended period of time. All right, so in the target, we've got an alloy, primarily tungsten, but you got a little bit of rhenium there. The purpose for that alloy, if you remember from last semester, there's a couple of things. One, provides more strength, but it doesn't really go into, the textbook doesn't really go into what that means. And that is that tungsten is very brittle. It'll pop, right? If there's enough shock to it, it'll break. It's very brittle. So it provides some strength there, right? So the target material, specifically the tungsten, if we change the target material, we change everything except for two things. That's the minimum energy of the brems spectrum and the maximum energy of the brems spectrum. But everything else changes all the way across the board very dramatically. Unless you work in mammo, you're probably never going to use an X-ray tube that the primary target material is tungsten. It is not tungsten, I'm sorry. Is not tungsten. Mammo uses molybdenum in a lot of cases, totally different imaging characteristics, but the only thing that you're shooting through there is soft tissue, right? So that's what they use in a lot of cases in a mammo target. So the effects on the characteristic spectrum is also going to be changed. Remember that what holds the electrons into their specific shell, the arrangement of protons specifically, but protons and neutrons, right? So you've got a strong positive charge in the nucleus, so naturally the closer those electrons are to the nucleus, the stronger they're going to be held into place, right? So if you use fewer protons, then you're going to have less of a charge, and it's going to be more loosely bound. So brems spectrum, you know, if we could increase the gold, that'd be great. But what's the hazard in changing the gold? It melts quite easy, right? And then, you know, you might have meth heads coming in stealing your x-ray tube, you know, because of gold. So you can't use gold. Tungsten is not too far behind it, but molybdenum and rhodium are way down here. Okay? So when we're talking about the anode, everything except for the induction motor, which is a stator, a stationary equal stator, and it does not rotate, everything else rotates. So we also talked about last semester the anode Hill effect and its effect on image quality, and that is that we're going to have some emission differences between the cathode and the anode into the x-ray tube. At full exposure, the density differences are minimal, and to your eye, unless it's very dramatic, you're probably not going to see the differences. They exist in emission, but in as much as recreation of the image, you just don't see them all that much. So we'll talk about that, and there is a sharpness of recorded detail difference also, and it's exactly opposite of the density or emission issues. All right, so on the anode end of the x-ray tube, the emission increases and your sharpness decreases. So on the, oh, did I say anode end? What did I say? Anode end, okay. It's exactly opposite. So on the anode end of the x-ray tube, the emission decreases and the sharpness increases. On the cathode end of the x-ray tube, emission increases, sharpness decreases. Okay, so we'll talk about that throughout the semester as well. So, and we just talked about all that. Okay, so also though, in the protective housing, we've got a number of different things. Remember, if we're using an x-ray beam that is at 70 kVp or above, we have to have a minimum amount of filtration. That amount of filtration is 2.5 millimeters of aluminum or more, right? So that's the floor. That's not the maximum amount of filtration that you can use. That's the minimum amount. So you have to have 2.5 millimeters of aluminum equivalent. So it's not really aluminum, but it's aluminum equivalent. And remembering that you know, everything is radiolucent, right? Just different degrees of radiolucency until we get to true radiopacity. So the glass or the metal housing provides some filtration. The oil provides some filtration. Protective housing also provides some filtration. So that's all types of filtration, but as a type of filtration, we have two different types of filtration. We have inherent filtration and we have added filtration. And we said last semester, and it's going to hold true for this semester too, that inherent filtration, we're going to call anything that you have to legally make an x-ray, which means that in order to make an x-ray on the x-ray tubes that you use, which I'll shoot at 70 kVp or higher, then you're going to have how much filtration? 2.5 millimeters of aluminum, right? Equivalent, right? So each one of those things goes into that 2.5, as does, after it comes out of the housing, you got the collimator housing, and the mirror provides some as well. So if by the time the x-ray beam gets through all that stuff, it is the same amount of filtration as what it would be if we used 2.5 millimeters of aluminum, then how much do you have to add to it? That's a trick question. None. You've accomplished your goal. You're at 2.5 millimeters of aluminum or equivalent. But what if, after it goes through all that, it equates to roughly 2 millimeters of aluminum? What do you have to have? An additional 0.5 millimeters of aluminum. Still inherent filtration. Even though you added that, it's still inherent filtration because you have to have 2.5 millimeters of aluminum to legally make an x-ray. Okay, so that's the definition of inherent filtration that we're going to use. If you can't take it away and legally make an x-ray, then it's inherent filtration, right? Also though, inherent filtration, if you remember, it doesn't stay the same throughout the tube life, because as we make x-rays, we create more heat, right? And eventually the filament's gonna burn out. Before it burns out, it's gonna vaporize, it's gonna coat the inside of the x-ray tube, and we call that tanning, which adds inherent filtration, right? You can't get into the x-ray tube and scrape that off. So even though we can't, we could theoretically reduce some of the other filtration to bring us back down to 2.5, that's never gonna happen. So with tube age, inherent filtration increases because of tanning, right? So very good. So types of filtration, we've got inherent filtration. Added filtration would be anything above that. So something that you would add would be something like compensating filters. Compensating filters, you don't see a whole lot anymore because our computer algorithm does a pretty good job of evening out tissue density differences. So you take a lateral C-spine on a patient. If you could see the lateral C-spines that we used to shoot on screens of films, a person with any kind of size at all, you just don't hardly get down to C7T1, right? But with the CR and especially the DR systems, you can see a whole lot better than what you used to. So the computer algorithm's kind of taken the part of our compensating filters, but in some cases we still do see them. Scoliosis series, and it's not really a compensating filter as much as what it is a radiation limiting device. It's kind of like the demographic that we usually shoot scoliosis series on are young women and girls with developing breast tissue. So we want to filter out as much of the x-ray beam as possible before the x-ray beam gets developing breast tissue, right? So it's really not so much for image improvement in that case as it is limiting radiation exposure to breast tissue. All right, so what does filtration do to the brems spectrum? Well, it decreases the numbers, right? Even if it only decreased the low energy photons, it's going to decrease the numbers, and it's going to increase the minimum energy, right? So on the brems spectrum, what you're going to have is a decrease in the height, but it's also going to take those minimum numbers and get rid of some of those. Okay, so the overall height is going to go down. It's going to get rid of some of the low energy, but with that, what you're going to have is an increase in average energy, right? So what you're going to have a tendency to do is kind of conflate a few things, all right? So we start talking about increasing the average, and where your mind might immediately goes with KVP. Okay, well, with increasing KVP, what do you get? You get an increase in peak energy, increase in average, increase in numbers. And then it might make a leap to generator type. So you go from single phase, three phase, you don't get an increase in peak energy, but you get an increase in numbers and you get an increase in average, right? So you got two different things that you get an increase in numbers, increase in average, and then you get to filtration and you're stuck on those two things, right? With filtration, you're going to get an increase in average, but you're going to get a decrease in numbers. Okay, so that's where you're going to have a tendency to trip up, is you're going to have a tendency to look at filtration. You're going to say, well, I got a better filtered beam, so I got a higher average. I got a better quality beam with increase in KVP and increase in generator type. Then naturally, I'm going to have an increase with filtration. What you're left with is more penetration, more penetrating x-ray beams, but you're going to lose so many numbers that you're going to lose exposure. Okay, so don't make that leap. With generator phase, KVP, both of those things go up, but with filtration, as we increase filtration, we're going to decrease numbers, even though we get an increase in average, and what we're left with is better penetration, but we're going to lose so many that we're going to lose exposure. Okay. All right, so collimators. We've got, collimators, another leap that you're going to have a tendency to make is what collimation does and what it doesn't do. So remember, X-rays behave like light in a lot of ways, and in some ways it does not, or they do not. X-rays do not. So with light, we can focus light, right? Laser beams are just focused light. We can't make an X-ray laser. We don't focus X-rays. We just block X-rays, right? So when we have collimation, what we're doing is we're blocking a portion of the X-ray. Now, it might focus your view and it might focus your eyes on a specific anatomy, but it doesn't take that beam and focus it down, right? It just blocks a portion of it. So it's beam restriction. It's not beam focusing. You can't focus the X-ray beam. Collimation is just beam restriction. You're restricting what you expose to the radiation, and therefore you restrict what's going to show up on the image receptor. So in our collimators, we've got two different sets of collimators. We got the one that you see. Those are the shutters that you actually visualize and make a square, a rectangular field. But you've got another set that you don't see unless biomed is in working on your machine. They take the collimator housing off. And what that is what they call a multi-leaf collimator. And a multi-leaf collimator is, let's see if I can kind of make this happen, is kind of like, imagine a cone of pieces of lead. And what the cone does is they kind of overlap, sort of like this, all right? So that if you open your collimators, first off, if you close your collimator, it looks like that, right? So nothing gets through the cone. But if you open your collimators, they kind of spread out and extend so that X-rays can get down through it. Now the shape and the orientation of your multi-leaf collimator, they stick up towards the X-ray tube, so they follow the divergence of the X-ray tube relatively closely, right? So they stick up towards the X-ray tube out of the top of the collimator housing. And as you open them up, they just kind of spread out a little bit. And as you close them, they kind of come together. The purpose for those is not really beam restriction as it is, and we'll talk about this later in the semester, as it is that they compensate for off-focus radiation. So off-focus radiation is any kind of radiation that's created anywhere aside from the focal tract. So we'll talk about that later in the semester. So beam restriction actually occurs with your shutters, the ones that you actually manipulate most whenever you see the manipulation of whenever you turn your dials or you push your buttons to increase or decrease your field size. Also, another thing some of you may have a tendency to trip over is what increase and decrease collimation means. You think of increasing something and naturally you think of it gets bigger, right? But with collimation, it goes in the opposite direction. As we increase collimation, we decrease field size. So increased collimation means to make the field size smaller. Okay? Decreasing collimation means to make the field size larger. So you decrease collimation, that means you're opening up your collimation. As you increase collimation, that means you're making it smaller. Okay? So filtration, again, what we see here is 2 millimeters of aluminum, 4 millimeters of aluminum. Notice it decreased the number of low energy X-ray photons that we created. Didn't change the peak energy. Didn't change the characteristic spectrum. We lost a lot of X-ray photons, and it pushed the average towards the high energy side. So that's the effect of filtration. The older the X-ray tube gets, the more we're going to lose in height, and the better quality X-ray beam we're going to have. Okay. So X-ray creation, remember we've got two different types of X-ray creation. We've got brems and we've got characteristic. With brems X-rays, it just means slowing down. So with slowing down, what we do is we send it, and we talked about this, I think, the week before last week maybe. So we send the electrons across the tube with a lot of energy, right? So a lot of kinetic energy they're carrying with them, and that's in the form of speed, and it slows down as it hits the target. And we're going to create an X-ray beam or X-ray photon that's proportional to the amount of energy lost. And we kind of drew this out last semester. And that is that, let's say our electron gets close to the nucleus of the atom. The electron is negatively charged, nucleus of the atom is positively charged. And we used the analogy last semester of gravitational pull, right? As a comet comes through, if it gets too close to Jupiter, Jupiter being a massive planet, then what could happen to said comet? It could change directions, right? It could even smack into Jupiter, but we're going to say change directions. So if it gets too close because of the gravitational pull of Jupiter, it could change directions. As it changes directions, it's going to lose some energy, and that's what we have in brems creation, right? So the electron goes around the nucleus of the atom, it slows down, and as it slows down, it's going to lose some energy, and we're going to create a brems X-ray photon. And a brems photon is going to be equivalent to the amount of energy that is lost, right? So if we send an electron into this atomic field, and it's got 100 keV worth of energy, your keV worth of energy, and it loses 99 keV worth of energy. It slows down that much, then the equivalent X-ray photon that we're going to create is going to be 99, right? So it lost 99, so we're going to create an X-ray photon equivalent to that loss. Incoming energy minus outgoing energy equals the energy of the photon you create, right? So then we go back to any brems spectrum. It doesn't really matter which one we choose, say this one right here. So what we get then are energy, the peak energy of the X-ray beam is equivalent to how much energy is available to lose. So in that example, I said 100 keV electron. Yeah, that's the energy the electron was carrying when it came through. If it's got 100 kVp equivalent worth of energy, how much can it lose? Kind of a trick question. Could it lose all of it? Yeah, it could. So you set 100 kVp and that thing comes through and it loses all of its energy, then your X-ray photon is going to be 100 kVp, right? So what you set in the kinetic energy on your machine, the kinetic energy that that electron is bringing with it, whatever you set on the X-ray, on your X-ray control panel, that's a maximum energy that you can get out of a brems spectrum, right? Out of that particular photon. But what we see, if you remember, before filtration, last semester I drew out the brems spectrum going all the way up to 0 kVp. Most of what we get, because of the structure, the atomic structure, most of the area inside of an atom is empty. There's nothing there, right? So it's not going to get close. Most of the electrons are not going to get close to the nucleus of the atom. So most of what we create are going to be very low energy, very low, unusable type low energy. So we run it through all that filtration and we come up with a brems spectrum that looks like this, right? But still, our average energy is going to be about 1/3 of our peak energy, right? So most of the X-rays that we create and emit from the X-ray tube, even though we sent it through filtration, they're still going to be low energy, about 1/3 of our peak energy. We're going to create, as a matter of fact, very few of the highest energy X-ray photons. Okay? So in brems, there's no real minimum energy. There's no limit to the maximum energy that we create. You know, if you could send electrons across the tube with 1 million electron volts, you could create 1,000 kVp worth of energy out of them. Your machines won't do that, but therapy will, right? So there's no real limit to the maximum. The only limitation of the maximum is what will your machine allow. And then it's represented in all energies. All right, so then we have characteristic, and characteristic is formed when we eject an electron. So we hit an electron with an electron, and if it ejects that electron, inner shell is the only one that we're going to focus on. It's held into place with 69.5 keV worth of energy. So if we hit it with a 69.5 kVp projectile electron, it could eject it, or higher. It could eject it, right? But it's going to want to replace that electron. So that electron that gets knocked out could vacate, and it could pop right back into place, and you're going to create an X-ray photon. And the energy level of the X-ray photon is going to be equivalent to the difference between two things. So with brems, it was the difference between the incoming energy and outgoing energy. With characteristics, it's going to be the binding energy of the electron that got knocked out minus the binding energy of the electron that's going to replace it. Okay, so a little mental exercise. It's bound into place 69.5 kVp or keV, right? You knock it out, what's its binding energy now? You knocked it out, what's its binding energy? Nothing, right? So what if it snaps back into place? You got 69 minus nothing, right? 69 minus 0 is 69, right? So let's say another unbound electron is just traveling through. It just went through the whole brems cycle, lost all of its energy, and it's just kind of hanging out there. You knock the one out, and it goes way off into the middle of nowhere, but you got this one electron that lost all of its energy, and it snaps into place. Well, what's it bound with before it snaps into place? Same answer, nothing. So it snaps into place, then 69 minus 0, you've got a characteristic X-ray photon created, and it is 69, right. So what if it pulls a K-shell down? K-shell binding energy is 12. Okay, so you leave with 69, right? So you got a vacancy at 69, and it pulls a L-shell electron down. L-shell held into place by 12. 69 minus 12 is 57, right? 57. So for whatever reason, we just focus on that 69. Unbound electrons snapping into place, 69 kVp characteristic spectrum. We do create characteristic in a lot of different energy levels, but the only one that we focus on is a K-shell and unbound. So 69 kVp is always going to be our recognized characteristic spectrum. So characteristic spectrum, we call that a discrete spectrum, and with the brems spectrum, we call it a continuous. All right. So characteristics, statistically, they say accounts for 15% of the beam. So really, the only way this makes sense to me is that, okay, we're accounting only for that inner shell electron ejection, right? But maybe 15% of the beam is actually characteristic if we consider every energy level. Because if you study the atomic structure, most of the atomic structure is empty. The nucleus is very small, and the electrons are in comparison to the overall atomic structure. And the electrons are so small, we don't even give them a mass, right? So we're shooting things that are so small they almost don't exist. And we're expecting to hit 15% of the time one of two specific things that are traveling really fast around the nucleus that are also so small they almost don't exist. For me, I can't make the mental leap that 15% of our X-ray beam is going to be 69 kVp characteristic. It just doesn't work for me. So, all right. Any questions? All right. Well, why don't we pull up there and we'll pick up there on Wednesday.